Hi, I'm Bob Pusateri, and welcome to the ABCs of BDCs, Big Data Clusters for Beginners. I hope you're having a wonderful time here so far at PASS Virtual Summit 2020, but please remember that there's much more to PASS than PASS Virtual Summit. PASS has local groups that meet all over the world. They have free one-day training events such as SQL Saturday. There are PASS marathon events, virtual groups, and plenty of other ways to get involved with the data community through volunteering. Please explore everything PASS has to offer at pass.org. Very briefly to introduce myself, as I said, my name is Bob Pusateri. I have been working with the Microsoft Data Platform and SQL Server for about 15 years now, but probably the most interesting thing you'll find on this slide is my contact information. You can find me on Twitter, I have my email there, or you can also go to my blog at bobpusateri.com and there's a contact page there as well. If you have any questions about this session, please feel free to reach out and I will do my best to get you an answer. We will be having a question and answer session following this presentation, but if you're watching this on a recording later and would like to get your own question answered, please feel free to reach out. I will also have this contact information up again at the end of the presentation. Now, if you weren't already aware, this presentation is part of the Big Data Clusters Learning Pathway here at PASS Summit. This is presentation number 2. You're here with me in the ABCs of BDCs. Earlier today, there was a session by Buck Woody talking about big data clusters architecture, the building blocks that make this all work. And later this week, we will have sessions from Dennis Torres talking about how you can leverage a data lake with your big data cluster, from Ben Weissman talking about how to actually build and deploy a big data cluster, and from Argenis Fernandez talking about storage technologies and how those apply to big data clusters. So what exactly is a SQL Server Big Data Cluster? I don't want to repeat too much of what was covered in Buck Woody's session because Buck did a tremendous job and got very deep, but I am going to touch on a few points, and I'm going to use his slides to do so because they were so excellent. Buck told us about how a big data cluster lives on a platform called Kubernetes. Kubernetes is a platform that provides a layer of abstraction between hardware and software, which we control through a tool called kubectl or kubectl. Here we have a Kubernetes cluster. We have multiple nodes, the big black squares there. These nodes can be either physical computers or virtual machines. Often they will probably be virtual machines. Kubernetes, the platform, is the gray box that spans multiple nodes. And then within the Kubernetes cluster, we have what are called pods, represented by the blue boxes, and containers, represented by the gray boxes inside of those blue boxes. Pods exist to keep resources together, and anything you do with Kubernetes actually occurs at the pod level. So you don't really touch the containers yourself. Kubernetes handles that for you. Off to the side, you'll see the 3 teal-colored boxes representing storage volumes. Because containers are often spun up and torn down very frequently, it wouldn't make much sense to have anything stored on them because that storage would constantly be having to be moved around. So instead what happens is the containers and pods connect to storage volumes where that data is actually persisted. And a storage volume would be something like a SAN or a NAS, for example. Buck also dove into the logical architecture of a big data cluster. There's a lot of components involved here, and all of them are living on Kubernetes. You can see we have in this diagram, we have our administrator on the right side of the screen. She's managing the big data cluster through the control service and through proxies. And on the left, we have end users. And end users are connecting to the big data cluster most frequently through the SQL Server master instance. They can also connect, however, through Spark. And we're going to talk about these components and what they do and how you connect through them in a little more depth. So here's another visualization of a big data cluster, and I've kind of taken Buck's slide and broken it down a little more. We still have multiple nodes. We have the big black box, which represents Kubernetes. Inside Kubernetes, we have kubectl, which is the software for managing the Kubernetes cluster. The orangish box inside that represents the boundaries of the SQL Server Big Data Cluster itself. Inside that, we have AZ Data, which is an application used to manage and create the Big Data Cluster. We also have Azure Data Studio, which is how we would most frequently connect to the big data cluster, and indeed that's what I'll be covering in all my demos. We also have web services that make parts of the big data cluster accessible. And then we have the core components itself. We have the master instance, the SQL data pool, the storage pool, the compute instance, and the application pool. Now, I am going to be talking most frequently in my demonstrations about the master instance, the data pool, and the storage pool. So let's dive in a little more on those. Now, the master instance is a regular SQL Server instance. It happens to be running on Linux, on Kubernetes, but it is still a regular SQL Server instance, and you can do anything on that master instance that you can do with a normal SQL Server. It exists to be the main endpoint for connectivity to the big data cluster. So you would connect to this master instance with Azure Data Studio or SQL Server Management Studio, just like you would connect to any other SQL Server instances. And indeed, if you're looking to do something like restore a database into your big data cluster, you do that on the master instance as well. The master instance will handle communication with any of the other parts of the big data cluster, and it also handles all the metadata that's involved, because there's metadata for HDFS for the Hadoop distributed file system that's a part of the big data cluster. There's metadata for external tables, which are heavily leveraged, as we will see in our demonstrations. And there's also shard maps for data that's in the data pool as well. So the master instance is doing a whole bunch for us. External tables are kind of key to big data clusters, as most of the data in a big data cluster will not reside on the master instance, but they will be represented on the master instance as an external table. If you're not familiar with external tables in Polybase, they are a tool used for exposing data through SQL Server that is physically located somewhere else. So this could be a CSV file located in HDFS. This could be another instance of SQL Server somewhere else. It could be an Oracle server, Teradata, MongoDB, Azure Data Lake, Azure Blob Storage. There's a lot of different things you can connect to via Polybase with an external table. And once your data is connected as an external table, you can query it just like it was any other table in SQL Server, and you can join it to regular tables in SQL Server as well. It is important to point out, however, though, that these are read-only tables. You can create statistics, but that's about it. You cannot insert, update, or delete data from them. You also cannot create indexes. All queries to external tables are real-time queries. There's no caching involved, just like with SQL Server. There's no caching involved there either. Any query you write will go hit the data and return results. Same things happens when you're querying data from an external table. All queries will hit that source system. Next, we have the data pool, which is a set of SQL Server instances, a pool of them rather, that provide storage and compute services. Now, you do not connect to the data pool directly in a big data cluster. The master instance will manage that connection for you. So you connect to the master instance, and the resources you access on the master instance may be in the data pool if you've put them there. The idea here is you can take large quantities of data and distribute them across this pool. So if you have a data set with, let's say, 10 million rows, and you have a data pool consisting of 10 SQL Server instances, each instance will have 1 million of those rows, give or take. When you issue a query against the data pool, the work of that query is then spread out and distributed across all those instances in the data pool as well, and then returned to you like a regular query through the master instance. Data in the data pool is similar to external tables. It is read-only, but this is a great place to use data for staging or caching and basing analytics-based queries off of there. And next we have the storage pool. And the storage pool is for all your non-relational data needs in a SQL Server big data cluster. The storage pool provides HDFS, the Hadoop distributed file system. It provides a HDFS cluster within the big data cluster. So you get this set of persistent storage across, again, multiple nodes that are represented to you as a single file system. So when you execute a query against a file, or probably more frequently a folder in HDFS, it's then being spread across all the machines in the pool that make it up. These would typically be things like CSV files or Parquet files, are probably the most common ones you'll see. Any data that is in the storage pool is accessible multiple ways. You can query this data through an external table from the SQL Server master instance. You can also query it through Spark. So you can have data sitting in this storage pool and access it multiple ways depending on how you really need. And now we've talked for a bunch, but this is a demonstration-based session, and demonstrations are much more interesting than slides, in my opinion. So now we're going to move to the demonstration phase, and we're actually going to see everything I just told you about in action. So please follow me, and we'll head over to the demonstrations. So here we are in Azure Data Studio, and I'm connected to a big data cluster, which I will show you in just a moment. But before we go there, I wanted to point out that you will want to download and install the Data Virtualization plugin for Azure Data Studio when you're connecting to a big data cluster. It provides some wizards and is very helpful because a lot of the things you do with a big data cluster do involve data virtualization. So there's a plugin containing some extra features that you'll want to have installed on Azure Data Studio. Now, to show you my servers here, as you can see, I am connected to a SQL Server Big Data Cluster. I've named it BDC. This is running in Azure on Azure Kubernetes Service. And just to show you around briefly here, if I right-click and go to Manage, it'll pull up the server management page that you'll see in Azure Data Studio for any other SQL Server database you would connect to. We have the Home and Databases tabs. We also have the SQL Server Big Data Cluster tab that is available because it's a big data cluster. Buck Woody went over this a little bit in his presentation, but just to show you, again, this contains, on this page, we have all the service endpoints, so all the boxes in the diagrams you saw earlier, all those different services, each of them has a different connection endpoint, and they're all listed out here in one easy to get place. You also have access to the Big Data Cluster notebooks for SQL Server 2019. So if you click here, you will see these are all Jupyter notebooks about different features of big data clusters. So if you have issues, if you're trying to do troubleshooting, trying to learn more, you can click on any of these notebooks. There is code, there is material, there's lots of great knowledge available in here, and this is all just part of Azure Data Studio when you connect to a big data cluster. You have down here at the bottom of the connections page, you have SQL Server Big Data Clusters. This will show you the controller for your big data cluster. You can right-click on that and go to Manage, or you can get to the exact same place by just clicking this Cluster Dashboard button on the management page. And if we click here, this will show us the status of all the services that are running, making our big data cluster possible. So we have the overview here, which is the top level SQL Server, HDFS, Spark, control service, gateways, applications. We can drill down into these. So if I click on SQL Server here on the left, it'll show me the status of the SQL Server portion of the big data cluster. So the master instance is up and running and healthy. The compute instance is also running and healthy. The data pool is running. It actually contains two instances, so it shows both of them here. Those are both good. Same thing with the storage pool, has two instances. That's running as well. HDFS, we can see the name node for HDFS. We can see the storage nodes. We can see Spark. So you can see the status of all of the components that make up your big data cluster in this one pretty nice dashboard here. Moving on to Object Explorer, as I would call it. Like I said, we're connected to BDC over here. There are some databases that are automatically installed as part of your big data cluster. So these DW configuration, diagnostics, and Q databases, those are databases you don't want to touch. Those are part of the big data cluster. Just leave them alone, let them do their thing. You have access to security like you would any other SQL Server instance. Same thing with server objects, but the new thing you have here is HDFS. This is actually allows you to access the HDFS file system in the storage pool that is part of the big data cluster. Now there's some folders here that are system folders. We have system, temp, and user, but you can actually go ahead and create your own folders and files, and they will be written, and you can do this all right through Azure Data Studio. So that's actually how we're going to start off this demo here, by creating some folders and uploading a file and just seeing what we have with data here. So I'm going to right click on the HDFS folder and select New Directory. You'll notice the box that pops up in the top middle of the screen there saying to enter a directory name. I'm going to call my directory Airlines. Hit enter and it will create the Airlines directory under HDFS here. I will do the same thing again with New Directory. I'm going to create a subdirectory under Airlines now called CSV. And there we have a CSV folder as well. Now I'm going to upload a file to that CSV folder. So I right click on it, hit upload files, and I'm going to upload the airlines.csv folder file to that folder. And there we have it. So now what can I do that I have this file sitting in HDFS on my big data cluster? Well, if I right click on the file, I have several options. Probably the simplest one here is called preview. If you want to just see the file in a text editor, Azure Data Studio will literally open the CSV file in a text window, so you can just read the contents of the file if you'd like to do it that way. You have another option here to analyze in Notebook, and what that will do is that will actually go ahead and create a notebook for you, put some Spark code in it to read back the first 10 lines of the file from the notebook. And I'll actually show you that in a moment, how that works. But the third option we have is to actually go ahead and virtualize the data, virtualize data from CSV files. And this is a feature of that data virtualization plugin I told you about earlier. This is one of the things it gives you, is it gives you wizards to help make data virtualization easier. So to start off virtualizing this file, we need a database to put it in first. We can't put it in any of these three databases. These are what helps run the big data cluster. So we're going to create a new database called Airlines Data. And we're just going to create a schema within that database called CSV. And I need to connect to the instance before I can create a database on it. So there we go. Let that run for a second. Now we have a database here called Airlines Data. I'll refresh and show you in Object Explorer, and as you can see, it looks like any other database you'd create on any other SQL Server. Now that we have that in place, we can actually go ahead and run the data virtualization wizard. So if I right-click on airlines.csv and say virtualize from CSV files, it'll take me through the wizard. It'll ask me what database I want to put it in, where I want to put it, or where the data is. It's in a SQL storage pool called SQL Storage Pool. Give the table a name, pick a schema name, CSV. The next page of the wizard will preview the data for me, show me what it's going to look like, so you can look it over that way. The next one will let you see the data types that the wizard has chosen for you, and you can modify if necessary. And then after that, you can either execute the script, or execute it, or to generate a script to do that for you. I've actually generated my own script, so we're going to go ahead and run that in a notebook instead. So I have this notebook here called Airlines Load, and this is all the notebook files I demonstrate during the session will be available at the end to download. So you can definitely try this on your own if you like. But what we're going to do is we're going to go ahead and create the external table for airlines.csv. Now, before we create the table itself, we need to tell SQL Server a couple things. We need to create an external data source to hold this data, and the source is already created. The source is the storage pool, but we need to tell the SQL Server master instance where the storage pool is. So we're going to do that by saying create external data source SQL storage pool with the location. As you can see, it's a URL style location here, SQL HDFS : / controller service / default. So that will tell the master instance where this file is. We also need to define a file format, and this is just like with any other external table that you would create with Polybase, is you need to define the format so Polybase knows how to read the file. So we're going to call this file format _CSV. It is a delimited text file with a field terminator that is a comma, a string delimiter that is quotes. If they're strings that contain a comma, they'll have quotes around them. And the first row is row number 2 because the first row is actually the header with the column name, so we don't want to read that and call that data. So the first row that actually contains data is row 2. So we've created our external file format. Now we need to create the external table itself. So we're going to call it csv.airlines. I'm using that CSV schema I created to help keep track of where this file is. As we get more tables with different locations, we'll want to kind of quickly be able to tell where that file is located. So this is a CSV file containing airlines. We have the columns, the data types. The location here is the CSV file. So we're saying go to airlines, CSV, airlines.csv. The data source is the storage pool, and it is a CSV file format. So let's go ahead and run this query. And this completes very quickly because it's not creating anything. It's just creating a external table and pointing to it. So if we go now to tables in Object Explorer, we'll see csv.airlines, and it's marked as being an external table, right? It does not exist on this SQL Server master instance. The data is elsewhere. So we can go ahead and query this now. So if I run this query here just to select the top 100 rows from csv.airlines, let's see if this works. Well, it didn't work. It generated an error, right? And if we read here through the error a little bit, we'll see it's a truncation error for row 4, column 7, okay, for the country column. Now, if you've done any work with Polybase or external tables, you've probably come across an error like this before. There's usually 2 big causes of errors like this. One of them is data typing, and the other one is usually line termination. So this is a data typing issue we have here. The error is telling us all about it. The problem is that the wizard does not sample all the rows in the table. It reads the first, I believe, 1,000 rows or so and tries to base the data types off of that. So if we have a improper data type, either from a bad estimation or from a bad data type given, which is what I did here because it's in row number 4, it will throw an error like this. What do? Well, we need to profile our data and figure out what the proper data type would be. And I'm actually going to do this in Spark because we have this data sitting here in HDFS, and we have Spark notebooks available to us, and we can connect through Spark as part of the big data cluster. So let's try that. So I have this PySpark notebook here, and I'm going to go ahead and just run this first cell of this notebook, and this is actually going to take a moment because this is the first time I'm running a cell in this notebook, and it has to start the Spark application and connect. So this will take a couple seconds here to do this, but when it's all done, it will come back with the top 10 rows of this file. All right, so it has created the Spark application, gotten everything initialized, and returned the first 10 rows of the file. As you can see here, it's got the column names from the header row and then the data, and it's divided it up all into the columns properly, so no problems there. That's great. Let's use some basic Spark commands just to kind of investigate this data a little bit. So this data is in what's called a data frame if you're not familiar with Spark, and on this first line here, we're defining a data frame called df, and we're telling Spark that we're reading from a CSV file with a header row, and the CSV file is called airlines.csv, and we want it to show the first 10 rows of the data frame. That's what this first cell is doing here. This next one is just going to print the schema of this data frame to show us about the data that's in it. Now you'll notice that Spark data types are not exactly like SQL Server data types. So airline ID, it's saying is an integer. Everything else it's calling a string, which everything else is a string here, but it doesn't give us length information. It's not like in SQL Server where it would be a char or a nchar 20 or nvarchar max or something like that. It's just a string with no length appended to it. So we're going to have to dig a little deeper. Now what I tend to do is I tend to use a package called pandas, which you can import in Spark. So I'm saying import pandas as PD, just referring to pandas as PD, and I'm going to create a pandas data frame using the df data frame, the one that contains the data, and there is a toPandas function on it. So when I run this, it will actually go ahead and convert that data frame to something that the pandas framework can use. Now, pandas has a function called info that I can run on a data frame. So I'm going to take my pandas data frame now, .info, and run this cell. And as we can see, this is telling us what pandas knows about it, which is it's going to tell us whether it's an integer or not. It's actually calling these strings objects now. That's how pandas works. Still not giving us length. So I have another script here in this next cell that will actually go and create a dictionary object and give me the maximum length of the string for every row in this data set. Now this can take a while if it's a really big data set, but the advantage here is you get your results accurately. So we know it was in the country column. I can see here that this little script I have has told me that the maximum value in the country column, maximum row length, is 37 in the country column. So clearly I was using a value of 10 before. That's not long enough. That's what's causing our truncation errors. I need to go back and change it to 37 or greater, and then hopefully it will work. The final little function I just want to show in Spark really quickly with pandas here is called describe. If you run describe on a pandas data frame, it will go and investigate the numeric columns in your data frame and give you some statistical information about it. So there's only one numeric column in this data frame, the airline ID, and we can see here that the maximum value for airline ID is 21,000. So while we can create this in an integer, we could also create it in a small int because a small int has a maximum value of 32,768, I believe. So we could create it in a small int column or an int column, but if we use the tiny int value, which has a maximum of 256, then it would not work at all. So now that we know that our problem is the length of the country column, I'm going to go back to my first notebook here where I'm running SQL. I'm actually going to drop this external table and recreate it with the proper column length. So now instead of country being varchar 10, I'm going to create it as a varchar 50. I'm going to run that query, recreate the external table, and now I can go ahead and query the top 100 rows just fine, no errors at all. So looks to me like this will work. If you really want to be sure, you can select star and see all the rows, but if you have a really huge data set, this might not be a great idea. It will only return the top 5,000 rows for you anyway, but as we can see here, we have 6,162 rows, return the top 5,000, and it gave me no errors. So now I can be confident that I have the right data types, that I shouldn't find any more truncation errors from this data set. Now that we have this external table correctly created, what can we do with it? Well, as I said, external tables are read-only, so we can't create indexes on them. If we try to do that, you'll get an error that indexes are not supported with external tables. Remember, it's coming from a different system. It could be a database, it could be a file like it is here, it could be something completely different. We don't know. So it does not allow creation of indexes. Similarly, this data, you can't update, insert, or delete from it. So if I try to issue an update query, that won't work either. But I can query anything with a select query that I can come up with. So if I want to see select star from csv.airlines, let's see the airlines that are listed in this data as being active with the country of Belgium, let's say. So it says 6 rows are available, and there we have it. So I now have this data in an external table that I am able to query with T-SQL as if it were in the relational database engine. But it's not, it's actually sitting in a CSV file on HDFS. So here's our next demo, and we're going to be continuing along with the theme of flights and airport-related data. But this time, instead of just taking some data and writing it out to a CSV file and querying from there, we're going to do some other things with it. We're going to write it to a Parquet file, see how that queries and performs, and also write it out to the big data clusters data pool and see what that entails. So last time, you saw me right-clicking on HDFS and creating some files, or creating some folders, uploading some files. This time I'm going to do the same thing via a script. If you remember earlier in my session and during Buck's session, he talked about how there were different APIs available for managing different parts of the big data cluster. And indeed, one of them is an API for managing data in HDFS. So rather than doing all that clicking, I've written a script in Python to do the same for me. So you'll see here I'm importing some processes, I'm defining some variables. I do have my password in plain text in a script in a presentation, which you should never do, but I'd like to remind you that this is a recording, and by the time you're watching this cluster and that password will be long, long gone. So what it does now is it'll run kubectl, get some information about what IP address it needs to connect to query that API, that web service, and then it will run curl, which is a utility for just going to a web address, sending a command. We'll run curl and create a file called flightdelays.csv in a CSV folder, in a flight delays folder in our HDFS here in the BDC, and it will upload the file from my local machine. So I'm going to go ahead and run both of these now, and it's just going to go ahead and take care of that for me. Probably one of the biggest downsides to this is that there is no status of the upload. So there's no percentage, no nice little bar crawling across the screen or anything to tell me that it's uploading or where it's at. It will just complete and be done. There's probably a way for me to add that feature, but I don't know that much Python to write something like that in there. So this file is about 136 megabytes. It's going to take a minute or so to upload. I should mention that the data I'm using in these demos for the airline themed data is all from a website called Kaggle.com. Kaggle is a great website if you want to get real data that you can experiment with, and there's notebooks on there showing you how to do it. So if you're trying to play around and learn about data science, Kaggle is a great place. And in the resources for this project, I will have links to where you can download these data sets yourself if you would like to try. Now we're just going to hang out for a minute and wait for this upload to complete. Okay, our upload has completed. Right click and hit refresh. We'll see we now have a flight delays folder, a CSV folder inside that, and flight delays.csv has been uploaded. So we've taken and uploaded this flight delay data into HDFS. Now we can go to our SQL notebook here, and we're going to start by creating an external table that just looks at the CSV file like we did for the airline data previously. So I'm going to use our database called airlines data that we already have. I'm going to create the external table pointing to flightdelays.csv, and I can go select the first 100 rows from that just to show you that yes, we really do have some data in there. So there we go. Now we're going to copy this data, this CSV file, into Parquet files. If you're not familiar with Parquet, it's a format that's very popular in data science. While CSV is a plain text, comma-separated file that you can open in a text editor and see the data and mess with to your heart's content, Parquet is a binary format, so you really can't open it in any kind of editor and look at it unless you like looking at a hex editor. But it does have several advantages over CSVs. It is a compressed format, so your data should be smaller. It is compressed in a column-wise manner. So if you think of a SQL Server column store index, the compression in a Parquet file is per column. So it's similar to a column store index in that regard. And the data is also somewhat indexed in a Parquet format. So you should get some size and some performance benefits from putting your data in Parquet. Parquet can also help you avoid issues with encodings. Sometimes if you're querying or reading data in from CSV files, you may have come across encoding errors at some point where it's expecting Unicode and it's not finding it, or it's finding Unicode where it wasn't expecting it, etc. Parquet takes care of this for you because it's encoding everything in binary on its own. So what we're going to do is we're actually going to create the Parquet files in Spark. So I have another notebook here called Flight Delays PySpark that will run. And this is similar to what we had before. We're creating a data frame that will look at the flightdelays.csv file. I just kicked it off, but the Spark application should have already been running. So there we go. It's returned very quickly, just the top 10 rows. We can see all the data in this file. Now this second cell I have in this file here is actually going to create the Parquet files for this data set. And you'll notice I said files, and that was not on accident. This code in Spark is going to execute in parallel across all the nodes in my Spark cluster. And if you'll remember from when I showed you the setup, there were two of them. So essentially what's going to happen is they're both going to look at this flight delays.csv file, split it in half. Each node is going to then go out and encode about half the data into a Parquet file and write it back to this directory. So we're saying df data frame. The name of the data frame is df. We're going to write it into a format that is Parquet with overwrite mode. So if the files already existed, they would be overwritten. They don't already exist, so that's fine. And we're going to save it into the flight delays/Parquet directory. And just hit start on that. This should actually go pretty quickly because once again, it's executing in parallel. So it shouldn't take very long at all to write this data out into Parquet files. There we go, it's complete. So if I right click on flight delays and hit refresh, you'll notice I now have a Parquet directory under here, and I have 3 files. There's a success file, which is how you can know that the writing of the files is done. And then the files themselves are named with GUIDs. There's a part 0 and a part 1 because there were 2 nodes working on this. So you have 2 files containing the information and the success file. Now that we've written it out into Parquet, we can go back and create an external table that will read the Parquet data for us. So we're going to say create schema Parquet so that we know in our database that we have, actually it's already there, so we don't have to worry about that, but this way we'll have a schema that says this is the Parquet version as opposed to the CSV version. We need to create a new file format because we're reading now not from a CSV file, from a Parquet file. So we need to define a file format, or an external file format rather, as a Parquet format. So create external file format underscore Parquet with format type equals Parquet, so it knows it's looking at Parquet files. And now we can go and create the external table just like the others. So create external table. Here's all the columns and their appropriate data types. We are looking at the Parquet directory, not a single file, but a directory. And if you do a lot of data science and analytics work, you're probably familiar with this already. But if you don't and you're working on learning this, this is something that's very common where you're not reading data from a single file. You're pointing some sort of analysis engine at a folder or at an entire tree of folders and saying, hey, go process all this, right? And you might have multiple nodes in that engine, so it's dividing up the work that way as well. But you're usually not looking at a single file when you're doing any kind of large-scale analysis. You're usually pointing at a folder or a tree. So that's exactly what we're doing here. We're now pointing at the Parquet folder, saying read all the Parquet files in this folder. That is our data. And we will go ahead and create that external table now. There we go. We have an external table. And now we should be able to just select the top 100 rows from the Parquet version of the flight delay data. And here we go, and it's returned it for us. We can see the data's there. Great. Now for our third act, we're going to do the same thing again, but this time instead of writing it out into HDFS, we're going to write it into the SQL data pool. If you remember, this is the pool that consists of multiple SQL Server instances, and the data is divided amongst them. So the data is now in a SQL Server as opposed to sitting on a Hadoop file system. Now, this is not on the master instance that we're connected to. This is on the nodes that make up the data pool, of which there are 2 of those as well. So we're going to start by using our airlines data database. We're going to create an external data source called SQL data pool that points to the SQL data pool. If you remember, we had one before that pointed to HDFS. Well, now we need a different one that says this external data is located in the data pool. Once again, it looks like a URL. So we have SQL data pool : / controller service / default. So I'll run that cell. We have now created this external data source. I'm going to create a schema called data pool. So once again, we can tell where our data is being stored by the name of the schema that it's located in. So we have our schema, and now I'm going to create the external table that will reside on the SQL data pool. So we're calling this now datapool.flightDelays, and we have all our columns defined in here with the data source equals SQL data pool, and we have a different argument here now you'll see with distribution equals round robin. This is how the rows are distributed against the multiple nodes making up this pool. I'm saying do it in a round robin fashion, so it's going to write a row to one node, then go and write a row to the other node and go back and forth. You can do that. You can shard on a particular column value if you'd like to do that, or you can replicate where all the nodes will contain duplicates of the data. But round robin is usually going to be your most popular choice for this. So we will create this external table now residing on the SQL data pool. This will take just a second because the master instance is actually going out and coordinating with the members of this pool. Hey, you're going to have a table here now. So there we go. Now that we have this table created, and I should refresh my tables up here so you can see, we now have csv.airlines, we have csv.flight delays, the CSV version, datapool.flight delays, the datapool version, and Parquet.flight delays. So you can see the schema names are coming in handy here. We can tell which copy of the data is where. So now I'm going to actually copy the data into the data pool, and this is just a simple T-SQL statement at this point, right? We're inserting into the datapool.flight delays table from the csv.flight delays table. And this will take just a moment while it loads that data up across those machines. So now that's done, and we've loaded about 1.9 million rows in just under 35 seconds. We copied that data from the CSV files into the data pool, into both of the SQL Server instances that make up that pool, got about half of each of those rows. So now that we've done that, we can actually go ahead and count the number of rows in the data pool. And that returns very quickly to show the same number of rows that we loaded, so that's great. Another neat thing we can do with the SQL data pool is actually push a query down to the individual instances that make up that pool and return separate results. So that's what this next cell is doing here. I am using execute and saying select count star from data pool.flight delays, but I'm using this at data source SQL data pool keyword, keyword in the syntax, which is saying return these results on an individual basis from each member of that pool. So if I run this query now, we'll get two result sets back, one for each node in that pool. One has 938,422 rows, the other has 938,320. So relatively equal, and that is how the data has been distributed against the members of this pool. So now we've taken the flight delay data set and we've loaded it into the big data cluster in three different ways, right? We've attached it as a CSV file, we've converted it to Parquet and attached it as a set of Parquet files in a directory, and now we've loaded it into the SQL data pool as well, where it's actually residing in a relational database. I thought it might be cool just to do a relative performance comparison against those three different methods. So my first query here, I'm going to select count star from csv.flight delays. I would expect this to be the slowest simply because it's actually reading from a text file, and that returned in about 6.8 seconds. We'll try it now with the Parquet file, and that returns much more quickly, 0.4 seconds, right? Because not only is the Parquet file compressed, it's indexed, there's also likely some metadata in there saying how many rows are in the file, so it doesn't actually have to count them all, it can just read the metadata. And then finally, we'll select count star from the data pool version, and that's even faster. That returns the same answer in 0.2 seconds. So you have different ways of accessing the same data, and of course, they all come with their own different performance characteristics and implications. And finally, one thing I haven't done in any of my examples so far is actually joined between these sources, because all these external tables coming from different locations can be joined together just like any other tables in a SQL query could. So I have a little query here that is joining the Parquet version of the flight delays data from this demonstration with the csv.airlines external table from the first demonstration I showed you. We're going to join those together and do a little select here on some flight delay data. And as you can see, that returned in about 1.3 seconds, and it has seamlessly joined them together like they were all sitting on the same server. So of course, they're virtual data instead. So that concludes this demonstration. There's one more little demo I'd like to show you here, because if we go back to the slides very quickly, I have this one slide I showed you from Buck Woody's presentation. And we've talked about a bunch of things here. We've talked about the master instance. We've used the compute instance, whether we realize it or not, because it's managing everything for us. We use the data pool, and we've had a bunch of data sitting in HDFS locally. But what we haven't touched is any external data, and that's easy to work with too. So what I have is I have a Azure data lake with some parking ticket data loaded into it. Parking tickets actually from the city of Chicago for the year 2003, I believe. And we're going to access this data externally. So I'm going to mount it into my HDFS as if it were there, but it's not. It's a Linux file mount, or the equivalent of like a Windows drive mapping. And we can do this all visually through Azure Data Studio. So if I right click on HDFS, I'll get an option to mount HDFS, and that'll pull up a wizard here with some characteristics we have to enter. So I need to give it a path. Where do I want to mount it into HDFS? I'm just going to call it parking tickets, if I can spell. I have to provide a remote URI, so where is this data at, which this will vary based on your source, but I have an Azure Data Lake version generation 2, so that's the path to mine, and then I have to provide credentials, of course, for that, which you can't see. Hit OK, and it will go through and try to mount this data. And there we go, it's been mounted. So now if I refresh my HDFS, I'll see a folder in here called Parking Tickets, CSV 2003. It's broken up by month, but here we have parking ticket data that I've mounted from an external Azure Data Lake. And we can browse it very quickly here. We can click, preview. It will pull it back and read this data, and then I can access it any other way that I've already showed you, right? I can write Spark queries for it. I can attach it as an external table. I can do whatever I like. So there you have it. This has been a brief demonstration into some of the capabilities of SQL Server big data clusters, and I really hope you enjoyed these demonstrations. All right, that wraps up the demonstrations and wraps up my presentation as well. I have just a few more housekeeping items, and then we can move on to the question and answer portion. First of all, if you liked what you saw and would like to learn more, I have some helpful resources here. Microsoft has an excellent workshop on big data clusters architecture that's available on GitHub. It's completely free, and it's about a day's worth of material you can work through to understand more about the architecture of big data clusters. If you'd like to learn more about Kubernetes, Anthony Nocentino is a fantabulous resource on Kubernetes, as is Klaus Aschenbrenner, so I have links to both of their blogs here as well. Similarly, if you'd like to learn more about big data clusters, some great resources for that are Mohammed Darab and Ben Weissman. They both have tremendous material on their blogs, so I've linked to those. And finally, if you would like the materials from this session, you can go to bobpusateri.com/r/ABCs of BDCs. This will forward you to my GitHub, where you can download this slide deck as well as all the notebooks that I worked through for the demonstration portions. I'd once again like to remind you that this is part of a 5-part learning pathway here at PASS Virtual Summit 2020. This was part 2, so if you liked what you saw and would still like to learn more about big data clusters, there are 3 more sessions. You can tune in to Dennis's session talking about data lakes specifically with big data clusters. Ben Weissman has a session talking about how to build and deploy a big data cluster, and Argenis Fernandez is going to talk about the storage aspects of it. Thank you very much for attending. I really do appreciate your being here watching this. Finally, I would appreciate your feedback as well. Session evaluations are being conducted for PASS Virtual Summit 2020, so there is a session evaluation link on the left-hand side of your navigation bar. I would very much appreciate it if you would click it and please give me feedback. Also, if you provide feedback before 5 p.m. on Friday, you will be eligible to win prizes. And in closing, thank you once again for attending. Here is all my contact information on the screen, as well as the URL to get to the resources for the presentation on my blog. And with that, we will move into the open question and answer portion.